Good evening, everybody. It's great to see you all here. Our guest of honor tonight, Zhu-Xi Luo. She did her undergraduate degree at Fudan University in Shanghai area, and her degree is in economics. The major was international economics and trade. But physics was very fortunate that she decided to diversify, and she did a PhD in physics at University of Utah. During that time, her first association with KITP started because she was a graduate fellow, which is a program we have where 6 to 8 students come for 6 months from all over the world to grow a bit in their career and their education during their PhD. We have a meeting on Thursday where there are 48 applicants for the next round of graduate fellows, so that awaits us to look over. Then we were also very lucky, KITP was very lucky that Zhu-Xi came back to the campus for postdoctoral work, which is work that you do, research work after you graduate with your PhD. Time to just do research. And she was at 3 years at KITP with first support from Simon's collaboration on ultra quantum matter, and then from the Quantum Foundry at UCSB. She has just moved to Harvard, moved on, but we were lucky that she was visiting Caltech just for this month and for this little period, and drove up today so she could speak to us. I think that you can get a very good idea of what physicist does from her webpage. First of all, Zhu-Xi has written 20 papers, but on her webpage you can see what it's more like doing physics. She has stack of papers about this high from scratch paper and things she read during her graduate career. So that's one of the things that's part of daily life of physicists, scratch paper. A lot of it, a lot went into the wastebasket too at certain points. So let us get entangled.
I guess I'll climb up. Thank you so much, Mark, for the very nice and long introduction. I'm very happy here for the first time, to present my recent research to non-physicists. So please feel free to interrupt me anytime during my talk if you feel something is hard to understand. So my title today is to generate entanglements through measurements, a time to tear down and a time to build. So I'll start by a casual self-introduction. I will skip the first line since Mark has already covered it. So my research interests mostly focus on condensed matter theory and its intersections with high energy theory and quantum information. And as for hobbies, I do aerial silks during my leisure time, and Jenny sitting here is my classmate. I enjoy playing with jigsaw puzzles, and it's not showing here, but I also like to read books with my toddler son, who is sitting here. Okay, I wonder if we can adjust the screen such that it moves a little bit to the left. But I guess my main stuff are in the center of the screen, so it should be fine. Here's a preview of my talk, the preview of the logic. I'll start by introducing measurements and how they can affect the systems being measured, and in particular, how they can affect the entanglement properties in the system. And by affecting entanglement, they can make a system topological. And by doing that, they can help improve quantum computation. You might not know these terms yet, but this will give you a very rough idea. I will introduce these terms later in my talk. Okay, measurements. Measurements happen every day in your life. You measure length. You measure temperature of your food using a thermometer. A police officer might measure your speed with a laser gun. You can measure your grocery, the weight of the grocery using the scale. But most of the times, measurements are harmless in the sense that they will not affect the system being measured. But there are also cases where they can. For example, if you see a police officer measuring your speed, you may slow down. So after the measurement, your speed are no longer the same. It's no longer the same as what you had before. But this is not the kind of effective measurements that we will discuss today. A more scientific example would be the measurement, like making the measurement is already observing the system. So it's the measurement itself that changes the system, not observing it. That's true. But that's not a scientific example that we will discuss. Yeah, okay. So a more scientific example would be the measurement of the tire pressure. So if you want to measure the tire pressure, you need to have some air escape the tire for the gauge to measure. But once some air escapes, the tire pressure decreases. So it changes the pressure being measured. Another example is that when you see something that is non-luminous, it means the object actually is reflecting the light. If that object is like a building, an apple, or a bug, it's probably fine. But if that object is very light, like a very light particle, like an electron, the fact that the light is shining on it may change its velocity and position. So in this sense, having a measurement, so if you see this particle, the particle has been changed. Okay, the effect of measurements can be more dramatic in the quantum systems. The previous examples were in classical systems. So the fact that you're all here, I guess that means you're interested in theoretical physics. And if you're interested in theoretical physics, I bet you have heard about the cat being both live and dead, and how measurements can make the wave functions collapse. So getting tired of cats, today I'm going to use bears. So consider a quantum bear in a quantum woods. So there are 3 roads diverged in a quantum woods. So you know there's a bear, but you don't know where it is. So the state of the bear can be described by this function, this equation. So bear can be either on the left, on the right, or in the middle. So since we don't know where it actually is, it's a summation of these 3 possibilities. And this notation of a short vertical bar and this angled bracket, this combination is called a ket because it's half of a bracket. It's just a notation. We also have a bra, which is the left angled bracket plus a vertical bar. It's just a notation. It tells you whatever is inside this ket describes the state of the system. So it's not a number. Okay. Suppose the bear had some preference over which road to choose. So we can have 3 potentially different numbers, C1, C2, and C3. And then initially the bear is in this state, which we call a superposition state. By superposition, I just mean a summation of these 3 possibilities. So if there is one word that is most important in quantum physics, I would say that's superposition. It makes all the difference. And then if you want to really know where the bear is, you send some people down the road to check. You perform a measurement. And then say you see the bear on the left road. After this, your state of the bear has collapsed down to this. So now you only have one possibility left. You have permanently changed the state. You no longer see the possibility of you can no longer see the other 2 possibilities. So in this sense, the measurements have changed the system. Okay. And one can use this quantum state to calculate various properties of the system. And one important property of a quantum system is called entanglement. It's a key feature of quantum systems, and it basically describes how independent the subsystems are. To quantify entanglement, people define something called entanglement entropy. It's a non-negative number, so it can be either 0 or positive. So qualitatively, two subsystems, say I have a big system like this, and I separated it into two subsystems, A and B. And we call A and B, they're not entangled when the state of the full system can be separated into a product of the state of the two subsystems. Namely, the information of the whole system is separately encoded in the two subsystems, but not in their relationships. It's like you flip two coins, then the probability of having two heads up is equal to the probability of having one head up times the probability of having the other head up. So the results of these two flippings of coins are independent. So that's when the two subsystems are not entangled. So here is one example of quantum coins. So up and down means heads and tails. So since it's a quantum coin, it can have superposition. Suppose it's in this superposition state. So A and B just means the two coins. So they can either have one up, the other down, or both down. So one can easily observe that no matter what happens to the first coin, the second coin is always down. So one can easily extract the state of the second coin out of the parenthesis, and we get this. So the second coin doesn't care about the first coin. Okay. Another name of the quantum coin is a qubit. It's just a name. Okay. That's when we say the two coins are not entangled. So the two subsystems will be entangled if the state cannot be separated into this form. One example is this. Say we have, again, two quantum coins, but now in this state. It cannot be separated. So it actually, it's like twins. They decide to have matching outfits. So if one of them wants to be up, the other must be up. One of them wants to be down, the other must be down as well. So if you know the information of the first coin or the first qubit, you automatically know the information of the other qubit. So in this way, we say the two subsystems or two coins are maximally entangled. And we will call this state the twin state, just for convenience. And now, how can measurements affect entanglement in a system? Let's start from the twin state, this one that I introduced in the previous slide. Now we try to measure the first qubit, or the first twin, or the first coin, whatever. If you measure this first qubit, you will see it's either up or down with probability both 1/2. Say you get up. Then after the measurement, your state collapses into this state. And with this form, it can be easily separated into this, just up times up. And for this state, there is no entanglement between the two coins or qubits. It's like you from California and someone else from Massachusetts, you vote for the same presidential candidate on the same day. That doesn't make you two entangled. You just accidentally vote for the same person. So there's no entanglement left after you measure subsystem A. So this is an example where measurements can destroy entanglement in the system. So initially, you have maximal entanglement, and after measurement, you get none. Okay. So to prepare for the next slide, I will introduce 3 more twin states. So in fact, we know there are in total 4 different twin states where the two twins are maximally entangled, and they have these forms. So these two are like the matching twins, while these two are like the angry twins, which decide to always wear the opposite thing. Okay, and there are some relative signs in between, just telling you that there are some preferences over whether being up or down. All right, so in the previous slide, I described how measurements can destroy entanglement, but in fact, they can also create entanglement. So this is a picture. So the camera is measurement. The wavy lines, the yellow and blue wavy lines are entanglement. These arrows are qubits or coins of a quantum system. So the measurement can either destroy entanglement or add entanglement into the system. Okay, so now let's describe how measurements can create entanglement. let's say we start from the unentangled state, where both qubits are up. And now we measure A and B, or A or B, to see whether they're up or down. So after the measurement, you will always get up because the state only has up. So the measurement does nothing. After the measurement, the state is still this. The system remains unentangled. But instead of doing this, if we do some other measurement, we ask the question, which twin state are you in? Is the system in? So then the answer would be definitely one of these 4 twin states. But no matter which one, the state will always be maximally entangled. So after this measurement, we get an entangled state, even if we started from an unentangled state. In this way, measurement can create entanglement. So we can see it's very important to ask the correct question. If you measure something, you might do nothing. If you measure something else, you can entangle the system. It's like this. So you put a basket of clothes into a washer. If you open the top cap, you get a red dress. If you open the front door, you get a dragon. So it really depends on like which door you're opening, which sort of measurement you're doing. Okay, so we have seen that measurements can change entanglement in the system. Now, what is good for? Okay, so the previous several slides have been a little technical, so let me just come to logic again, such that we're not very completely lost. So I have introduced what measurements are, how they can affect the systems being measured, and measurements can generate entanglement. Later, I will describe how they can, in fact, generate long-range entanglement. I will describe what that is later. And after the long-range entanglement is generated, it would mean the system now enters a topological phase. And using the topological property of that system, one can help with quantum computation. So I will start by now introducing quantum computation, just to motivate things a little bit. So there are many big companies, corporations are working very hard to trying to realize quantum computation. We have Google and Microsoft here in Santa Barbara, and we also have Amazon not far away in LA. Very roughly, quantum computation is to use the power of superposition to do computations. Very, very roughly is the fact that you have these different numbers, C1, C2, and C3, in a quantum state. Okay, compare with the classical state. In a classical state, you will only have one possibility. So you remove this middle and the right, and you only have the left, and the C1 will be just 1, the number 1. That's a classical state. Now, in a quantum state, you can have this superposition. You have all sorts of possibilities. The fact that you have all these numbers means that you have more things to twin, to manipulate, to control. That gives you a better computational power. Is it good? It's definitely good. Otherwise, people won't be investing in them. But how good are they? So first of all, quantum computers can solve all problems that that classical computers can solve. This is again because if you take this state, you remove the middle and right, you're just left with the left, which is the classical state. So by training some numbers, you can always go back to a classical state. So you can do whatever classical computation can do. And now, quantum computers can tackle certain problems much better, much faster than classical computers do. Certain problem is a bit vague, but let me explain. So it's very hard in general to prove that quantum computation can do something that even the smartest design of classical computation cannot do. Well, practically, it might be very hard to find a good classical algorithm, but you don't know whether it's just it doesn't exist or it's just you're not smart enough. So it's hard to prove something is not possible in classical algorithm. But so only in very special examples you can show, in fact, theoretically, that quantum computers are much, much better. But so in general, quantum computers are better, but sometimes they're only somewhat better, not significantly better. So this is a figure of the computational power of a system versus the number of qubits in the system. So say for classical computers, it may only do some okay job. And when you have quantum computers, it may do some somewhat better job. So say classical computers have this scaling of t, say t is the number of qubits, while a quantum computer can do t squared, which is better, larger than t when t is big. But sometimes quantum computers can also do exponentially better, so e to the power of t. So the difference between this exponentially better and polynomially better might not be very obvious in the case of small system size. But when you have a bigger system size, you will see that this distinction between t and t squared is actually not obvious. T squared is still larger than t, but the difference is not that big. While for this exponential function, I should have written e to the power of t, not e to the power of x. But so we can see the exponentially better is really significantly better. So in certain systems, quantum computers can do this significantly better job, while in many other cases, it's only polynomially better. But as long as it's better, it's worth studying. And in reality, if you want to do quantum computation, you always need to face some practical problems. So the quantum states are very vulnerable, more fragile than classical counterparts. And the biggest challenge is error and the decoherence. Basically, your system of interest, your quantum system, will inevitably interact with the environment. And the environment will uncontrollably change your quantum system permanently. Thus, like the quantum system will lose the information it stores, and there will be errors in the computation, etc. So if one ever wants to do quantum computation well enough, he or she will need to resolve the problem of decoherence. He or she will need to control the decoherence and the level of error in the system. So how do we do that? One idea is to use topology. So what is topology? So topology properties are those properties that will not change if you smoothly deform the system. Namely, if you do not do something drastic such as cutting or gluing the system. For example, this mug is of the same topology as this donut, because you can smoothly deform one into the other. So also from this perspective, a cow, let me play my GIF on my laptop. A cow is just topologically the same as a spherical cow. And in fact, from the topological perspective, everyone in this room has the same topology, unless you have ear piercings or more nose piercings, etc. So unless you dig a hole, you use scissors and glue, you won't change the topology. So the idea is one can use topological quantities to encode the information in a quantum computer, because that way local errors, local deformations will not be able to change your topological information. The topological information is robust against local errors. So in this way, we can have the potential to do good quantum computation. This is a side remark. So topological systems are interesting by themselves, even without considering the applications to quantum computation. So topological phases of matter in condensed matter systems, they are very quantum and weird, and they comprise a huge field in physics research. In particular, they can host emergent quasiparticles with fractionalized charge and statistics. By fractionalized charge, I mean, for example, in certain systems, we find that the charge of the quasiparticle of the excitations in the system can be only 1/3 of the elementary charge of an electron, or they can be more, say E over 10, E over 5 or something. It's very weird. And such topological systems can exhibit long-range entanglement. I will define long-range entanglement soon. Okay, let me first tell you about short-range entanglement. So we have learned that entangled states are those that cannot be separated into this form, product of states of subsystems. So short-range entangled states, they're entangled, of course, so they cannot be separated. And in addition, they can become separable. They can be turned into this state using local deformations, local transformations. It's like you can massage this state just like you massage a doll. And then after that massaging, that local transformations, if you can change your state into some separable state, then I will say your system is short-range entangled. And in such systems, the entanglement entropy, the quantity that measures entanglement, typically has this form. So alpha is some constant, and L is the size of the boundary between the two subsystems A and B. So intuitively, this is because if the entanglement is short range, it means the main contributions to the entanglement comes from the boundary which separates A and B. So the boundary connects A and B. Okay. Now long-range entanglement. So long-range entangled states are those that are entangled, of course, so it's not separable. And it cannot become separable after local transformations. Oh, my son gets excited. Sorry about that. So they cannot be separable after local transformations. And there's one measure of long-range entanglement called topological entanglement entropy, which is a brilliant idea by Gustav Preskill and Levin-Wen back in 2005. So what they do is that you can partition your system, say your full system is this square. You can partition it into 4 parts, A, B, C, and D. And your topological entanglement entropy is defined in this way. So it's a summation of entanglement entropy of this region A with entanglement entropy of B and C minus the entanglement entropy of this A and B, this whole region, minus BC minus AC plus ABC. So the reason why it's arranged in this way is because the following. So recall that for short-range entangled systems, the entanglement entropy will be proportional to the size of the boundary of the system. In this case, the boundary of A is the length of this, is the boundary between region A and D, plus the boundary between A and B, plus the boundary between A and C. So it's a summation of these 3 boundaries. And you can write similar expressions for all the other terms, and it turns out that this particular combination cancels out all these boundary sizes. So if you have short-range entanglement, if you only have short-range entanglement in this system, you will get S topo equals 0, because all the short-range entanglement, by construction, they're canceled. So if you ever get a non-zero result when you compute this S topo, it means you will have long-range entanglement in this system. So, okay, that's the definition and how to quantify quantum entanglement, long-range entanglement. Okay. Now I'm going to introduce my research. Although I have introduced all the main necessary concepts, it might still be harder to understand. So fasten your seatbelt. So this is our setup. So what we are trying to do is to use measurements to generate this long-range entanglement, and hoping it can help us with the good quantum computation. So our setup is the following. We consider a 2-dimensional lattice. It's like a layer. And the lattice is of this shape, this honeycomb shape. It's really like a honeycomb. And we have the qubits or coins or degrees of freedom. They live on the dots. They live on the vertices of this honeycomb lattice. And then, as you can see from the figure, there are 3 types of links labeled by the colors, green, blue, and red. I just give them some names, X, Y, and Z, for convenience. So what we will, okay, let's zoom out this one honeycomb. What we'll do is to start from a state, where this is the same square there. I'm just zooming in. Starting from a state where each qubit, each dot or each vertex here is a twin state with an external qubit somewhere. such that so each qubit will be maximally entangled with some other qubit outside the system, outside the lattice. That's my starting point. And now we do some random measurements. At each time step, near each vertex, I choose to measure one of the three types of bonds. So one of the three, X, Y, or Z type of bonds. With different probabilities, Px, Py, and Pz. And these three numbers sum up to 1, such that I always measure some bound. I just don't know which one I measure. And after measurements, the qubit in the system will disentangle with the external qubit and entangle with an internal neighboring qubit. So let's say we want to measure the bond between the yellow dot and the blue dot. So initially they form twin states with some external qubits, but after measurement, recall that measurement can generate entanglement. So they generate entanglement between these two coins or qubits, and also remove the previous entanglement between this qubit and the outside qubit. This way, we generate entanglement within the system. And therefore, the entanglement in the system increases. And these three types of measurements on these three colors of bonds, they do not commute with each other in the following sense. If you first do one type of measurement and do another, it's different from that you first do another and do that original one. So they do not commute. That makes these different types of measurements compete with each other. So when you have different magnitudes, different choices of this Px, Py, and Pz, since they commute, they might give you different final results on this quantum system. For example, say at some time, you have these two entangled with each other, forming a twin state, these two in a twin state, and these two in a twin state, and now you decide to measure these two. You ask which twin state they are in. Then you're entangling these two. And the green one, the purple one are now on loose ends, so they will entangle with each other. So by doing this additional measurement, you're changing your entanglement structure in this system. And when you twin this Px, Py, Pz, you basically twin how probable it is to measure this type of bond, or this type, or the other type, etc. And the main results, when we twin different Px, Py, and Pz, we get two different types of phases. So at this point, we have Pz equals 1 and Px, Py equals 0. At this point, I have Px equals 1 and Py, Pz equals 0. And this is Py equals 1, Px, Pz equals 0. It turns out when one of these three probabilities dominate, I will have one type of phase where there are two topological qubits, so two good qubits protected by topology that can potentially be used in quantum computation. While when the Px, Py, and Pz are really comparable, namely they compete wildly, then in this region we have another quantum phases of matter which exhibit a log violation of the short-range entanglement form. Recall again, the short-range entanglement form is like entanglement entropy is proportional to the size of the boundary of the subsystem. Now, but in this phase, the entanglement entropy is not of that form. It's like log of L instead of just proportional to L. So log of L is larger. So it's a violation of that linear form. So in both phases, although they behave quite differently, they both have non-trivial topological entanglement entropy. Recall, topological entanglement entropy is a feature of long-range entangled states. So meaning that both phases have long-range entanglement. So this is a plot of the topological entanglement entropy with respect to the twinning probability of the measurements. So we have two different phases, but each one has long-range entanglement. That's my last slide. Here's a summary of the logic again. We described our measurements. We described how the measurements can affect the quantum system, and in particular, how they can generate long-range entanglement, and how long-range entanglement can make the system topological and can help with quantum computation. These are my brilliant collaborators, postdoc at KITP and faculty at UCSB, and this is my where my funding comes from. All right, with this, I will thank you.
Thank you, Zhu-Xi.
Sure.
Bet we have some questions. We just need one to start off. Right here.
You know, I've been reading about this for many years now.
Mm-hmm.
And my question really is there, after all this time, is there a single example of a problem which classical computing cannot solve in a reasonable time and quantum computing can?
Yes.
What is it?
It's the Shor's problem. It's the factorization of prime. So the factorization of integer into a product of primes. So
that actually works on a quantum computer?
Yes, and it's.
Well, that pretty much would destroy all the or break encryption on every computer on Earth. Huh?
Exactly. Yes, that's actually why many big corporations are interested in quantum computation.
So I'm allowed to be skeptical then. Huh?
Sure, of course. Yeah. Oh, actually, I have one more slide. So in case you're interested in quantum computation, here are two further readings, further watchings. So this is like a 15-minute video by Scott Aronson. Like both are leading scientists in the field of quantum computation. So Scott Aronson is a professor at UT Austin. And here is a more 90 minutes talk by John Preskill, who is, again, also a leading scientist. And he talked about quantum computation, in case you're interested.
Thank you. Who's next? Yes, I'll hand this to you. So you have to pretend you're.
Okay. So here you are at this level, at this university, and you put all this work together, and just being here and watching it, even though I don't understand most of it, is very exciting. I'm just wondering what's happening all over the world with different companies who are creating those next computers, which are already probably created using quantum. Are there like thousands of people like you sitting in labs in these private corporations just like figuring all this out, and are you guys aware of each other, and are all the papers published, and is this just accelerating and we're all learning from each other? Because we're the university level, but what about all those private companies and the mastermind people that they've hired? How do you see that in the street?
So many PhD students and postdocs end up working for those companies. And yes, and in fact, so in this morning I was at a meeting at Caltech, and there are two speakers. There's one speaker coming from IBM, and yesterday there was one speaker from Google. So we meet at conferences and we talk to each other. So for people in the universities, we're probably more interested in the theoretical or formal side of the problem, while they're definitely the people in the corporations, they're more technical or realistic.
Very well be some of those people that have like cracked certain parts of this code to a level where they have to keep it kind of quiet. So we don't really know how far this information is.
Right. Some of their results are confidential indeed. Yeah.
We had a conference at KITP last week where there were 120 such people talking to each other for a week, 4 days, with refreshments and dinners and so on.
In one of your early slides, you showed how a measurement can destroy entanglement. And in the bottom half, you showed how a measurement can create entanglement. Well, destroying entanglement was easy to understand, quote, well-known, unquote.
Mm-hmm.
But could you elaborate a little bit more on how a measurement can create an entangled state?
Yes. Yes. So you basically ask the question. So instead of measuring whether a system, so say again, starting from this state, instead of measuring whether the qubit is up or down, you ask whether these qubits are entangled in this way, this way, this way, this way, or this way. But whichever way, the A and B are entangled. So it's like by asking this question, by construction, you're entangling this system.
You have to do more than ask the question. You have to.
Oh, you measure it.
You have to.
When I say by asking it, I mean measure it. Ask the system, measure the system, which one of these states they're in. But it's always one of these 4 states because they form a complete description of the possible states the 2 qubits can be in. So, yeah. Exactly. Right. Yes. We have to measure them as a pair to create entanglement. Yeah, it's like measure the relationship between the 2. Yeah. Yes.
Maggie.
What's ultra quantum matter?
What's ultra quantum matter? So ultra quantum matter is, maybe it's on my first casual self-introduction slides. It's about how quantum matter can intersect with other parts of physics and how they can be useful for technological application, etc. And also, ultra quantum matter are usually quantum matters that are strongly correlated. There are like a great amount of interactions between different parts of the system and highly entangled. The system is very entangled. And it's weird. They should be weird. Otherwise, it won't waste the time studying them. Yeah.
Maybe you define this, but what does local transformation mean? Does it mean that you're applying on like a subset of qubits?
What is local transformation? So, it can actually be understood very intuitively. It's just, so I have a system as big as this room. Local transformation would mean an action, an operation that only acts on, say, this region or some other region, but it never acts on like regions that are very far away. So the operation is local.
So where do you draw the line? Like, what operation is local? Is there some parameter that is associated with locality?
Yes, one can define that for sure. Yeah.
And regarding that, how to sort of measure to create entanglement, are you just projecting onto one of the 4 states and to create entanglement?
Am I just the what? The first?
Is the measurement just projecting onto one of the 4 states?
Yes.
Okay.
Yes.
So I'm having a hard time sort of interpreting the end result. Where do you see this going? Like, what are going to be the implications?
You mean the implications of
for quantum computing, like the?
So the logic is by making the system topological using measurements, you can encode quantum information in this topological systems. And once the information is encoded topologically, it's robust against all these local operations or local errors. So it should be good to use.
So can I interpret your result as sort of an improvement on like the feasibility of encoding the topological information?
So the idea of using topology to do better quantum computation is not mine, but my work provides a way to, like, it's an explicit construction to use measurements to like to realize this topological encoding of information.
Thank you.
I understood it as like a long-term.
It's good because long-range entanglement means the system is topological. Yeah, it's good. But it's bad in a sense that usually such systems are hard for theorists to understand.
So, long-range creating entanglement, what kind of distances are we talking about here?
It's like you have to know the global properties of the system. For example, I think I have a figure probably in the end. Let me try to. Oh, maybe this. So local data. So if you look at this donut or torus, if the information is just encoded in this region, it will be local. But if the information is encoded only along this loop or along this loop surrounding the whole, it will be non-local or topological. So you won't be able to change it or detect it unless you go through this whole thing. So you won't be able to destroy it unless you do some drastic things like scissors or glue.
So could this be used to transmit information because if you're entangling some distance, can you then use that as a means to transfer information instantaneously?
No. So entanglement is, so you're not really sending information from this region to another region. The fact that wave function collapse doesn't really mean you're really sending some particle from here to there. So what our logic is that we use this topological thing to encode information, but not to send. But maybe one can create some smart ideas to use topological properties to send information, but it won't be faster than light.
Okay, I think we should thank Zhu-Xi again. That was wonderful.